Greetings and welcome to week 7, unit 2 on instruction for analyzing. In the last unit, we tried to understand how to instruct for applying activities. Here we are referring to the cognitive processes of revised Bloom's taxonomy, and in this unit we will try to understand how to instruct for analyzing, which is the next level after apply. Now, analyze in revised Bloom's taxonomy, it focuses on breaking materials into parts to understand structure, relationships and causes. That is a formal definition of you can say analysis or analyze process. That is Anderson-Krathwohl who proposed the updating of original Bloom's taxonomy. They break analyze into 3 sub-processes. One is differentiate, that is separate relevant from less relevant or irrelevant elements. Then you organize, that is find or construct coherent structure or model. Whatever elements are there in the problem or problem statement, you try to build relationships among them and to try to build a model. Then the third process is attribute, that is you are trying to find out what influences the output, what doesn't, and to what extent it does is the one related to attribution. Let's look at some examples of learning outcomes for each category here. Differentiate, for example, differentiate signal sources from noise in measured data and justify which components matter for design decisions. Okay, that is you are trying to identify the elements, and you are having identified the elements, you are trying to say which is important, which is not important, or which is to be considered, not considered. That is differentiation. Then an example for organize. Organize the subsystems of a robotic arm into functional block diagram with a clear interfaces and responsibilities. Somebody describes a robotic arm saying that it will have these elements in that or subsystems in that. And in the organize activity, you are trying to link these elements and convert them into a kind of a block diagram, functional block diagram, and identify what is the interface between one element and the other. It can be mechanical connections, or it can be electrical connections, or it can be signal connections. The interface is, you are only focusing on the interface but not inside the element or subsystem. Attribute the root cause or causes of a mechanism failure using evidence from tests and propose prioritized corrective actions. Now, something went wrong in a given system, and then from the evidence that is available to you, you are trying to identify the particular cause or a root cause that led to the failure, and then based on that you are also proposing corrective action, what you should do. So these are the samples, and I am sure all these activities are involved in any engineering discipline. We now look at instruction strategies and activities. First for differentiation, what we are presenting is, if I have to perform differentiate activity in my subject, what kind of instruction strategies do I follow? That is, what are the type of activities that I want to do in the classroom or through the assignments or in the laboratory. So, for example, activities can be troubleshooting labs, data filtering exercises, reading tasks that require underlining essential claims versus side information. So, your task can be related to some laboratory activity or purely kind of data filtering exercise using some statistical methods to separate either trends from noise and so on, or reading tasks. You are provided some report from which you try to identify the whatever essential claims in that or some side information, but not the main information if you are able to separate that out. So, these are the types of exercises that you can do, and you can follow this particular instruction strategy to address differentiate. And what are the instructional components that we will use for it? We presented whole range of instructional component. The instructional components that can be used are paired think alouds, that is, two people sit together and they think aloud, they share with one another. Highlighting exercises from a given document or a given series of steps, you highlight what you consider the important ones. Guided questioning, which variables change output, which don't. If there are some inputs which do not change, obviously they will not have influence on the output. So you have to identify them. Or some inputs change extremely slow compared to the other ones. That means whatever effects they have, long-term effects. Okay, these are the instructional components that you can use to identify relevant from irrelevant issues. Then the tools that you use, obviously you have to have tools. One is measuring instruments if it is a lab, or the statistical analysis for signal to noise metrics that you want to use, and then sensitivity analysis in simulation. These are the tools that you would like to use, and obviously the students have to be trained in using these tools to perform the differentiate type of activities. Now we look at instruction strategies and activities, for the organize activity. What do we do in organization? Whatever elements that are presented to you, you are now, based on cause and effect relationship, you are trying to create some kind of a block diagram and focusing on the interface between the elements. Now, what kind of classroom activities do we want to, we can plan? Progressive decomposition exercises. Give a complete device like a DC motor system. It will consist of a DC motor and several other elements around that. That is what we are calling as DC motor system, and ask students to decompose it into functional blocks, then refine interfaces and signals across iterations. Okay, you keep refining the interfaces between the inputs. For example, at the interface, initially we might have identified some electrical connections, possibly some we missed. So through series of iterations, you will try to identify all the details of interface. As I said, interface can be mechanical, electrical, or signal, which means electronic. Then constraint driven design. Present performance constraints, budget, size, latency, and have students recognize subsystem boundaries to meet constraints. So in some you have constraint always, design is always constraint driven. Which are these constraints? It can be budget, size, latency, all of them are constraints, and you are trying to find out what are the boundaries that exist in meeting these constraints. You are identifying them. Mapping between representations requires students to produce block diagrams, signal flow graphs, and the governing differential equation model for the same system. So these are the mapping that are the modeling that you have to do. And what tools and techniques do you use? Concept maps can be used, systems engineering diagrams like SysML, UML for visualizing relationships. Model-based tools, Simulink, Spice, to build modular models and show how submodules interact. Version design notebooks, so students can show evolving organization choices and rationales. Sometimes you go through a series of iterations before you arrive at the final one, and that means you have version design. So these version designs are recorded. Okay. So these are the tools that you can use to perform activities that facilitate organization or organize activities. Now coming to attribute, what instruction strategies you want to follow? Deconstruction. Activities should involve breaking down complex systems into their constituent parts, that you are identifying the constituent parts first, and then identification of characteristics. The student should be able to name and describe key characteristics, properties and functions of each component. Okay. Connecting parts to the whole. Students should be able to explain how the characteristics of individual components contribute to the overall behavior of the system. Let's say I identify 10 components and I first record what are the characteristics or properties and functions that I need to worry about in a given system. Then in the third, I can create a table. In the third column, we can say from your understanding, which part influences the output in what way, if you can record that. And then you focus on relevant attributes. It is important to guide students to identify the most important attributes for the purpose of the analysis. That is, one way to do is to prepare a table like that, and then you try to identify which is the most important one that influences the output. Okay. Now let us look at an example. What do you call? We are trying to say how do we provide instructional support for overall analyze for all the three processes. This is umbrella view. Then we will get into individual sub processes. Now the example is, we are giving an example now at the analyze level. Students are provided with the frequency response of a filter and are asked to compare different filter implementations, Butterworth, Chebyshev, elliptic, to achieve the desired characteristics. They should analyze the trade-offs between filter order, ripple and roll-off. Filter has these three characteristics. What is the filter order? Is second order, third order. You can have nth order filter also. And will there be ripple in the output or and kind of roll-off? And what is the roll-off of a filter? These are the basic characteristics of a filter. Then before they get involved with the actual analyze activity, pre-activity lecture, how do I prepare them for performing this task? That is, you present filter characteristics, thoroughly review the key characteristics of Butterworth, Chebyshev and elliptic filter. That means already the students either studied or have been presented the characteristics of Butterworth, Chebyshev and elliptic filters. So you are reviewing those characteristics and for example, order and its relation to roll-off, a ripple, the pass band and stop band ripples, and transition bandwidth, phase response, whether it is linear or linearity. And then you go through trade-off, explicitly discuss the trade-offs involved in filter selection. Sharper roll-off requires higher order. If you want as close as possible to a kind of a complete rectangle with vertical boundaries, then you require higher and higher orders. Ripple allows for sharper roll-off but introduces signal distortion. Okay. If there is a ripple, that is, certain filters you can have very sharp roll-off, but it can lead to in the pass band you can have ripple. Linear phase response is crucial for preserving signal shape but can be harder to achieve. Okay. So these are the trade-offs that exist that students need to know, and then we look at also application examples, provide concrete examples of application where each filter type is most suitable. For example, Butterworth for audio due to flat pass band, Chebyshev for applications where some ripple is acceptable for faster roll-off, elliptic for demanding applications where sharper cutoff is crucial. Okay, and so the tools that we use for that are guided practice or worked out examples given by the teacher. Provide a worked out example where you analyze the frequency response plots of different filter implementation and explain how to determine the order, ripple and roll off from the plots. Then you have comparative table. Create a table template that guides students in systematically comparing the filter characteristics. Sorry, this example has to be in some field and the example has to be presented in detail, and then so we are presenting one example from electronics discipline or analog electronics where you teach filters in detail. It may be not that interesting for people, for students and faculty who come from other disciplines. One can create examples from each discipline separately. Obviously, in a unit like this, we cannot present examples from all disciplines. Then you do the scaffolding activity. Start with simple scenarios, comparing only two filter types and gradually increase the complexity. So this is scaffolding if you want. Depending on the students, if you think your students can skip some of the steps, you can skip. Tools and resources, you use simulation software and you provide reference material, and then you have online calculator tools. Introduce students to online filter design calculators that can help them determine component values for different filter implementation. There are such online calculators for filters are available because filter design is some very common activity an analog circuit designer will have to indulge in. And after that, you also go through feedback and discussion. Formative assessment, it's mostly Provide opportunities for students to receive feedback on their analysis before submitting the final assignment. This could involve in-class exercises, group discussions, or online quizzes. And then you can have peer review, have students review each other's analysis and provide constructive criticism. Or class discussion, facilitate a class discussion where students can share their findings, challenges, and insights. One thing, whenever we have presented a fairly large number of steps involved in facilitating the students to experience the analysis process, that too the total analysis process. And it may look very daunting when you look at so many steps involved. First of all, depending on the kind of students you have, what you have done earlier, some of the steps can be omitted. And also, it depends on the kind of resources that you have, the time you have at your disposal. Sometimes this kind of exercises can be shifted to a laboratory where resources can be made readily available. It doesn't have to be classroom with a blackboard or a whiteboard. Okay, so instruction can take place in the laboratory. So the teacher will have to be the judge what is the best he can do for this, but the analysis activity has to be experienced by the student in some form or the other. Now we come to the three. If you want to focus on differentiate, how do I provide the instructional support? Here we will only present general teaching strategies. Differentiate involves distinguishing between relevant and irrelevant parts, determining important features and noticing differences and similarities. That's what the differentiate activity means. And for this, we are doing structured comparison frameworks. That means you have to identify elements and keep comparing them. Comparison tables provide students with templates for creating tables to systematically compare different elements. The tables should have clear categories for comparison. See, comparison, if you look at, many of these things are also the activities that belong to understand category. But hierarchically, analyze is above understanding. So any activity that you do at a particular cognitive level or its sub-process, all the cognitive processes which are below that, hierarchically low, are implied in that. Okay. So obviously you are doing that activity. Comparison table in a way strictly belongs to understand. But you have to understand things before you can indulge in analyzing process. Then you can use Venn diagrams. Use Venn diagrams to visually represent the similarities and differences between 2 or 3 concepts, components and approaches. This is one of the tools. If it is necessary, use it. Otherwise, you don't have to use all of them. And then you have decision matrices. These are useful for evaluating different opinions against a set of weighted criteria. They force students to explicitly assign importance to different features. See, all these features one may not find when you are doing a very simple exercise. But if you are doing a more complex exercise, which is also the requirement of if you are talking about PO 1, program outcome 1, if you realize that the goal is to solve complex engineering problems, how do you prepare for that? So obviously by taking a more complex example and making them go through all these processes. Now, further general teaching strategies to support differentiate activity: explicitly define criteria, because you are now differentiating elements. You need to have criteria to differentiate them. Clearly state the criteria that should be used for comparison. This helps students focus their analysis and avoid irrelevant details. Provide examples of what constitutes a good or a bad score for each criterion. Discuss the relative importance of different criteria. That is your weighting. Now, these steps that we are showing are indicate how to perform to explicitly define criteria. Okay. And sorting activities provide students with collection of items, circuit components, data points, research articles, and ask them to sort them into categories based on defined criteria. This forces them to actively differentiate. So you are giving them experience by providing some details about all the elements. Present mixed set of relevant and irrelevant information and ask students to identify and discard the relevant parts. You are preparing them for that. You can create such examples and give them experience of identifying relevant and irrelevant parts. Then you can also use highlighting and annotation. Encourage students to actively highlight and annotate text, diagrams and data to identify key features and differences. Teach effective annotation technique using different colors for different types of information, writing concise summaries in the margins. You have a whole bunch of things, and maybe each student even can find his own method of annotating and highlighting. Find the difference exercise. Now, having done all this, you have to now find the difference. Present students with two versions of a system, circuit or a design that are subtly different. So you present two different representations or designs of a system. Ask them to identify the differences and explain their impact. This sharpens their attention to detail. Okay. It all depends on what kind of case studies that you create. Very small difference and students should be able to identify. Show a working design and a faulty design. Have students troubleshoot to find the difference. This can be done in the lab or as an exercise in the classroom with two designs presented. You are trying to identify the difference between them. Identify the most important prompts. Instead of simply asking students to describe the features of something, ask them to identify the most important features and explain why they are most important. Again, please, I have to keep reminding you several times. When I am giving you a long list of general teaching strategies, these are all the things you can potentially use. What things are adequate for your particular problem that you are doing, the teacher has to decide. You can use case studies and scenarios. Present students with realistic case studies or scenarios that require them to differentiate between relevant and irrelevant information to make informed decisions. The whole idea is you are trying to prepare the students to the idea of, given some information, how do you differentiate between relevant and irrelevant elements. They can be components, they can be arguments, they can be subsystems, whatever they are. Then expert modeling. Demonstrate your own thought process when comparing different elements. Think aloud as you analyze a problem, explicitly stating the criteria you are using, the reasons for your conclusions. So one of the ways of doing is expert modeling, that you present a case and the teacher goes through do all the exercise and keep speaking aloud, saying that This is what I am doing, this is what what happens, why this is important, not important. If you are able to present a complete case study like that while talking aloud, then the students may understand what is involved in the whole exercise. Then progressive complexity, which is like scaffolding. Start with simple comparisons and gradually increase the complexity of the material. And feedback and iteration, provide regular feedback on students' ability to differentiate effectively. If you are sitting in a lab, a large group, of course, whenever you scale up large number of students, it is always a challenge to how do you provide feedback and help the students to iterate. Challenge assumptions. Encourage students to question assumptions and explore alternative perspectives. This can help them identify subtle differences and nuances. That is one way. Ask them to challenge the assumption involved. They may be able to come with some saying that no, I don't agree with a particular assumption because of his reasons, whatever he explains. And here teacher should remember to emphasize the importance of clear communication and justification of choices throughout the process. This is a very idealistic way of doing things, and then to fit it into the timelines that we have, the teacher will have to find. These days plenty of tools are available in the open source or in the otherwise. So depending on the resources available, you have to converge on to what exactly you want to do with respect to the exercise. And this kind of exercise doesn't have to be done for every topic. The whole idea is to give them, analyze belongs to what generally is called higher order thinking. And training students in higher order thinking is a requirement officially. Though everybody says I am training my students in higher order thinking, but I have not seen any place where they follow some well-defined processes for facilitating the students to think at this level. Now we come to the next one, the organized activity. The general strategy is concept mapping, which we have already looked at how it is done, what it can do, and classification and categorization. These are, again, classification and categorization actually belong to understand category. And drawing a concept map is also understanding category. Okay? But you have to perform these activities to go to the next stage of pattern recognition. Present students with data sets, graphs or diagrams and ask them to identify patterns, trends or anomalies. This also can be considered as an understand activity. Provide guidance on how to use statistical tools or visual aids to identify patterns. Encourage students to explain the significance of patterns they identify. Relate patterns to underlying principles or theories. Okay. Then you can use hierarchical structures or matrices and tables, case studies and problem solving. Each one is a particular method. As I said, you need to only use if it is required or relevant to the particular exercise that you are doing. Another method is case studies and problem solving. Present students with case studies are real world problems that require them to organize information and identify relationships to develop solutions. If you are able to collect such case studies and keep them ready, you can show them. Guide students through the problem solving process. You can use visual aids and graphic organizers of any kind to help students organize information and identify relationships. In a way, concept map is a graphic organizer. Okay, mind maps are various fishbone diagrams and so on. And you can also convert into collaborative activity, which makes it easier when a small group of students work together to organize information and identify relationships. You can also do scaffolding or guided practice. That is a method. If you feel it works better for your group of students, use it. Start with simple tasks and gradually increase the complexity. In all this, if you notice, these are all student-centric activities. These are not teacher-centric. Teacher is acting as a facilitator, presenting a case, asking them to do something, and then is giving feedback, or maybe you can keep conducting a what you call formative assessment like quizzes and so on. But the actual engaging with knowledge is not passive, where students are actually working on it. That gets their attention much better. If you are a passive listener, it is easy to lose attention of the students. If student is not paying attention, whatever you do as a teacher is of no consequence. Okay, so it is advantageous for the teacher to indulge in student-centric activities like this. By implementing these strategies, you can help students develop skills they need to effectively organize information, identify relationships, and make sense of complex systems. That is the what you call organized sub-process of analysis. Now we come to the teaching strategies to support attribute activities. Attribution, you are trying to find out which influences more, what is influencing the output at what level. You are attributing, say, this variable x is influencing the variable y output. That's the kind of, that is attribution. The way you look at attribution in engineering, we will talk like this. If it is a humanities and social science subject, we use different terminology, but it is to talk about attribution. In humanities and social science, we will ask question, what is the author is trying to say, or what prompted him to say that, this kind of thing. Okay, but anyway, we are presently worried about engineering subjects. Then you look at component spotlights, declare time to in-depth discussion of the properties and characteristics of individual components. This is what we are saying, teaching strategies. Then what if analysis. Encourage students to ask, what if I change this component, and predict the effect of overall system. Simulation and modeling, which is a well-known thing. Emphasize the use of simulation tools to explore the relationship between component attributes and system behavior. Diagramming and labeling. Encourage students to create diagrams and label components with their key attributes. That is excellent way of engaging the students. Focus on why. Continuously ask students, why does the component behave this way? Or why is this component important for this function? So focus on why. Systematic analysis. Guide students to follow a systematic approach to analyzing complex systems, breaking them down into smaller and more meaningful, manageable parts. This is something that we do in all sub-processes of analysis. By focusing on these attribute activities and teaching strategies, you can help students develop a deeper understanding of how individual components contribute to the overall behavior of complex, let's say, electrical engineering systems, because we have taken for detailed example from electrical engineering, but similar exercise can be done from any branch of engineering. In summary, emphasizing analysis experiences in undergraduate engineering programs is crucial for developing well-rounded, capable and responsible engineers who can solve complex problems, design innovative solutions, communicate effectively and adapt to the ever-changing world of engineering. This is what many of the we are insisting all this through the POs already. Okay, so you will be able to meet multiple POs if you incorporate one or two analysis exercises or activities in your course. It empowers them to understand the why behind engineering solutions, not just how. Okay, and in the next unit, we will try to understand how to instruct for evaluating. The next level cognitive process is evaluate. We will look at how to instruct for that. And thank you for your attention.